Okay, so today we're going really small.
Okay.
Like really, really small.
All right.
We're talking molecules moving and spreading out.
Okay.
Like, you spray perfume and it fills a room?
Right.
Or if you drop food coloring in water and it, like, disperses?
Yeah. Yeah.
That's diffusion.
It is.
And the cool thing is,
Yeah.
there's actually math, like a whole mathematical rule book, that explains how this happens.
There is. It's pretty neat.
It's called Fick's second law.
Uh-huh.
Ready to dive into that?
Let's do it.
So, like, first things first.
Yeah.
What exactly is diffusion?
Okay. So, imagine a room, right?
Okay.
And it's full of air molecules.
Okay.
And these molecules are bouncing around like crazy.
Like all over the place.
Exactly. Like a room full of tiny bouncy balls.
Gotcha.
Now, let's say we introduce something new, like perfume molecules.
Okay.
These perfume molecules, they're also going to start bouncing around.
Bumping into everything.
Yep. Bumping into the air molecules and each other. And over time, all this random motion makes the perfume molecules spread out.
Okay.
So they move from where there's a lot of them.
Like where you sprayed it.
Exactly, to where there are fewer of them.
They spread out until it's like all even.
Exactly. That's diffusion in a nutshell.
So it's like everyone's just bouncing around until they're evenly spaced out.
Yeah, that's a good way to visualize it.
Okay, so that's like the basic idea.
Yeah.
But to really get into Fick's law,
Mm-hmm.
we need to get a little more technical.
A little good.
You mentioned this thing called a control volume.
Right. A control volume.
What is that exactly?
It's basically just an imaginary box.
Like in the room.
Yeah, like a little cube in space. And we use it to keep track of how many molecules are entering and leaving this box over time.
Oh, okay.
And Fick's second law, at least in one dimension, gives us an equation to describe this.
Oh, here comes the math.
It states that d, c dt, the change in concentration over time equals d, the diffusion coefficient, multiplied by d squared c dy squared, the second derivative of concentration with respect to position.
Ooh, okay.
It sounds complicated, but it's not too bad once you break it down.
Okay, yeah, let's break it down.
All right, so the d, the diffusion coefficient, that basically tells us how easily something spreads.
So like perfume would spread faster than honey.
Exactly. Perfume would have a higher diffusion coefficient than honey.
Okay.
Now the second part, the d squared c dy squared.
Yeah, that one sounds really complicated.
It's just describing how the concentration changes over distance.
Okay.
Like imagine a hill.
Okay.
A steeper hill means the concentration changes a lot over a short distance.
So it's like how quickly those perfume molecules are moving from crowded to less crowded areas.
Yeah, and how that changes depending on where you look in the room.
That makes sense.
So that's Fick's law in one dimension.
One dimension.
Yeah.
But the world isn't flat, right?
Right, exactly.
We live in 3D.
There's 2 dimensions.
So how does Fick's law work in 3D?
Well, it gets a little more complex,
I bet.
but the basic principle is the same.
Okay.
We just need to account for changes in all 3 directions.
So instead of a line, we're thinking about a cube.
Exactly, and that's where the Laplacian operator comes in.
Laplacian operator. That sounds intense.
It sounds scary, but it's just a mathematical tool.
Okay.
It's denoted by del squared,
Del squared.
and it basically combines the changes in concentration in all 3 directions, x, y, and z.
So it's like adding up the changes in each direction.
Yeah, exactly.
Okay, and does the Laplacian like change depending on the shape we're looking at?
It does, yeah.
So like
Like, for a simple box shape, we use Cartesian coordinates.
Cartesian.
Yeah, but if we're looking at a cylinder, like a can of soda,
Uh-huh.
we use cylindrical coordinates.
That's cylindrical.
And for a sphere, like a ball,
Spherical.
we use spherical coordinates.
Okay, so no matter the shape, Fick's law can still help us understand how stuff spreads.
Right, it's incredibly versatile.
So, like, how is this used in real life?
Oh, tons of ways.
Like what?
Well, think about pollution.
Okay.
Fick's law helps us model how pollution spreads in the air and water.
So we can predict where it'll go.
Exactly, and understand its impact.
And then hopefully find ways to stop it.
Right.
What else?
Another really cool application is drug delivery.
Drugs, like medicine?
Yeah, understanding how drugs diffuse through tissues helps scientists design better ways to deliver medicine to specific parts of the body.
So it helps the medicine get where it needs to go.
Exactly.
That's amazing. Anything else?
Well, in material science, knowing how heat diffuses,
Heat.
yeah, thanks to Fick's law, we can design better materials.
Like what kinds of materials?
Everything from computer components to home insulation.
Wow, so this law is like working behind the scenes everywhere.
It really is.
But are there like any limitations to Fick's law?
That's a good question.
Like, are there times when it doesn't work perfectly?
There are, yeah, because Fick's law assumes diffusion is only driven by random motion and differences in concentration.
Okay.
But in the real world, things can be more complicated.
How so?
Well, things like electric fields or chemical reactions can also influence how things spread.
Oh, I see.
And Fick's law works best when the environment is uniform,
Uniform meaning?
meaning everything's the same throughout,
Okay.
but a lot of real-world situations are more heterogeneous,
Heterogeneous.
meaning the material or conditions can vary, which can affect diffusion.
So Fick's law is like a good starting point,
Yeah, it's a foundational principle.
but scientists are constantly working to refine it.
Absolutely. Ongoing research is pushing the boundaries of our understanding.
In what kinds of areas?
Well, for example, in nanotechnology.
Nanotechnology, that's like super tiny stuff.
Yeah, at those really small scales, diffusion can behave differently.
Wow.
And also in biology, where complex interactions can influence these processes.
So there's still so much more to learn. Well, this has been an incredible journey into the world of diffusion and Fick's second law.
It has.
We started with bouncing molecules,
Mm-hmm.
then delved into some pretty complex math,
We did.
and then connected it all back to the real world.
Absolutely.
It's amazing how this law is working all around us.
It is, isn't it?
So before we go, I have a question for you to think about.
Okay.
Considering how important diffusion is, what other everyday examples of it can you find?
Good question.
Keep that curiosity going, folks. There's always more to discover.
Definitely.
That's it for this deep dive.
Thanks for having me.
Always a pleasure.
Likewise.
See you next time.
See you quiet.